Zoom is getting started. Okay. So I'm very happy to introduce our speaker today, Chris Davies, who's visiting us from University of Leeds, where he's a full professor now in theoretical geophysics. He was a Green Scholar at Scripps Institution of Oceanography in San Diego, where he met Anne Pommier. I met him probably before that, maybe when he was a steady Dornbos Memorial Prize winner in 2016. He won an award from the Royal Astronomical Society in 2014. He's now a member, he's a fellow of the Royal Astronomical Society as a geophysicist. He's the deputy director of the Leeds Institute of Fluid Dynamics. So that's pretty sweet. He's going to tell us today about magnetic fields. Hooray. So Chris, take it.
Thank you, Peter.
Oh, one last thing. The schedule today is full, but he's here till Thursday. So if you want to meet with him, and I know he wants to talk with more people, let me know, or Ann know, or stop us, and we'll set something up. Okay. All right.
We actually met in the French Alps, Peter, on a month-long workshop on dynamo theory. Thanks very much for the introduction. Thank you for the invitation. Thanks also to my collaborators and to our funders, NSF and NERC, for making this work possible. So what I'm going to talk about, broadly speaking, is global magnet. It is going to take me the whole time to get used to this thing, by the way, so bear with me. I'm going to talk about the magnetic fields, the global magnetic fields that are generated in deep planetary interiors that ultimately permeate the silicate shell and are observed at or above planetary surfaces. And I'm going to focus on three terrestrial bodies, the Earth, Mars, and Mercury. And the way I'm going to try and tie them together are through these things called stable layers. These are regions in the liquid iron core that are not participating in the field generation process. And I'm going to argue that these layers are important for understanding the magnetic field signatures that we observe. So we'll start with some observations. So these are the salient observations I want to address for Earth's magnetic field. On the left-hand side, you're looking at the radial component of Earth's magnetic field at the surface around about 20 years ago. So green is field lines pointing into the Earth, purple field lines coming out of the Earth. And, it's got the structure that we know and love, this dominant dipolar configuration, resemblant of a bar magnet that's centered at Earth's center. But it's also got these characteristic non-dipolar structures. Maybe the pointer is not pointing, or maybe I'm in the wrong place to point. I don't think so. It's all right. I can get on without it. Oh gosh. It's got sort of characteristic non-dipolar features. It's not a perfect bar magnet, and this is reflective of the process that's generating it. The other salient observation of Earth's magnetic field is it's very old. So what you're looking at on the right-hand panel is the dipole moments, the strength of the dipole component of the field as measured at Earth's surface versus age. And all the little dots are paleomagnetic observations. And the key point really is that the field is very old. It's at least 3.5 billion years old. It might be 4 billion years old. There's no obvious gaps in this record, so it seems to have been continually generated over this period. Mercury's magnetic field, at least superficially, looks a bit similar to Earth's magnetic field. It's got this dominant dipole configuration. It's slightly offset from the equator. But the main thing to notice about Mercury's magnetic field, at least its present field, which is being shown on the left here, is that it's incredibly weak. It's about 100 times weaker than Earth's magnetic field. It's also possible that Mercury's magnetic field is old. So we have observations from Messenger, for example, of a late dynamo, which is being shown in this cartoon here. Messenger has also observed crustal magnetization in a region that has been dated to about 3.8 billion years. So it's possible that Mercury's magnetic field is also long-lived. Mars, it has a very clear signature of crustal magnetization at the present day, strong magnetization in the southern hemisphere, relatively weak magnetization in the northern hemisphere, but it's not presently generating a global internally generated magnetic field. It's thought that the internal field generation stopped quite a long time ago, so somewhere around about 4 billion years ago. So the main question I'm trying to address in this talk, well, there are two of them. Why are these fields different first? And second, what do they tell us about the interiors of these planets? So the place to look when we think about generating global magnetic fields is in the liquid iron core. And the classical picture is that these fields are being generated by a dynamo process where we have vigorous turbulent motion of an iron alloy, and that the kinetic energy associated with that motion is being converted to magnetic energy by a dynamo process. This process, it's got a bunch of complexity associated with it. The planetary rotation gives rise to these helical structures that ultimately is responsible for generating the large-scale magnetic field. There's interactions between the magnetic force and the flow, and so on. But for this talk, really, the main point I want to make about the dynamo process is that it is reasonably well established through numerical investigations that the power that is available to the dynamo, which is being plotted on the horizontal axis, is a key controller on the field behavior that we observe. So this is an example showing how the power that's available to the dynamo controls the normalized internal field strength. So this is a wide class of numerical simulations. They've all been set up in various different ways. I'm not going to go through the details, but they've got different boundary conditions, whether they're fixed temperature or fixed flux. They're driven in different ways from the bottom, as you might expect from modern Earth, or from internal heating, as might be for Mars. But regardless of how you set up the model, you get a nice scaling relationship that shows that the field strength is proportional to the power that's available to drive the dynamo. And this suggests that when we are looking at why these magnetic fields are different, we should be focusing on how the dynamo is ultimately powered. And ultimately, the way that the dynamo is powered is by heat that's being extracted from the core by the overlying mantle. So it's nice to think about a global heat budget in this context. This is an example for present-day Earth. We've got a reasonable idea of how much heat is being lost through the Earth's surface, about 46 plus or minus 3 terawatts. And that heat is partitioned into various reservoirs within the Earth. There's heat production within the bulk mantle and the lithosphere. And then there are these two other heat reservoirs. There's what's called the secular cooling. So this is the heat that has been stored in the mantle since its formation, that is being gradually extracted. And then there is the heat that the mantle is extracting across the core mantle boundary. And this is ultimately what is going to power the dynamo. So there's various effects that can arise due to this cooling. One of them that is known to be significant is the growth of a solid inner core that I'm sure most of you are familiar with, but I'll just run through the basic idea. So you're looking at temperature on the vertical axis, radius on the horizontal axis. This is an example for Earth's core. So the melting point here is shown by the dashed black curve, and the core is cooling as heat is being extracted across the core mantle boundary. The core is cooling from the blue curve to the green curve to the red curve. And because the melting gradient is so steep, the first intersection occurs at Earth's center. So the solid inner core starts freezing. The core freezes from the middle. It grows out to its present day radius of about 1,221 kilometers. So why is this important for powering a dynamo? Well, you get a couple of additional heat sources. So in the absence of an inner core, the heat extracted at the core mantle boundary is just being balanced by the secular cooling, so the heat that's already stored in the core. But when you start growing an inner core, you get two additional effects. So the first is the latent heat. So this is the heat that is being released upon the phase change from the liquid to solid. And the second effect, QC here, is what's called the gravitational energy. And this is really important in the context of the Earth. So what's happening here is that the iron core is not pure iron. It's got about 10 weight% of lighter elements in it, silicon, oxygen, so forth. And some of these elements partition preferentially into the liquid phase as the solid freezes out. And so that's locally enriching the deep core in these lighter elements that are then free to rise, mix the core, and give us a source of compositional convection. And it turns out that these two power sources are very efficient at driving dynamo action and magnetic field generation. So with this sort of basic information in hand, one can start to make some crude links between the interior structure that we infer for the Earth, Mars, and Mercury, and relate these to the this interior structure to the power sources that are available to the dynamo. So the Earth's interior structure, well, it's cartoonized here. So the the core mantle boundary is at 3,480 kilometers. The core, liquid core, is about 2,300 kilometers across. There's an inner core, and one reasonable hypothesis would be that the growth of this inner core with the associated release of latent heat and gravitational energy is helping to power the relatively strong magnetic field that we observe. Mars's interior structure has been, I guess, sort of illuminated by the recent InSight mission. So the core is at about 1,800 kilometers from the center. There is as yet no evidence of an inner core. It's not to say that there is no inner core, it's just not been detected, but nevertheless, with the information available, a reasonable hypothesis is that perhaps the lack of the inner core is the reason for the failure of the dynamo, because at some point, as the core cools, the power to the dynamo decreases, and without these extra effects of latent heat and gravitational energy, the dynamo subsequently fails. Mercury's interior structure is still the subject of some debate. It seems that it's got a relatively large core, a thin mantle, and potentially a large solid inner core. And so one would expect that the large inner core, if we follow through this logic, would be helpful for magnetic field generation, which makes it curious as to why the field is anomalously weak. But there is an effect that has been sort of omitted from all of this, the discussion so far, and the effect that I want to focus on, which is these ideas of a stable layer at the top of the core. So in the picture that I've just discussed, what's happening is that the core is in turbulent motion everywhere, and the kinetic energy of this motion is being converted to magnetic energy by dynamo action. That's maintaining the field. But that doesn't have to be the case, and in particular, it is possible, and I'm going to argue probable, that the tops of the cores of Mars, Mercury, and Earth develop a conducting layer. So in this layer, the amount of heat that is actually being extracted from the core, which is Q, is less than the heat that is being conducted out of the core along its adiabatic gradient. And in this configuration, the temperature gradient is not steep enough to maintain convection, and we get a conducting layer in the top few hundred kilometers of the core. Perhaps it's our job to figure out how thick this layer is. And below this layer, there is the convecting bulk core that is generating the magnetic field. Inside this conducting layer, there's no radial motion. There can still be horizontal motion. There's no radial motion. And so this layer is not helping to generate our magnetic field. So the layer, this is going to be useful for later. There's two main properties of these layers that we characterize them by. One is just their thickness, delta. Again, it's our job to figure out how thick these layers are. And the second is some sort of measure of how strong is the stratification. And the classic measure, which I guess arises from oceanography, is n squared. This is the square of the Brunt-Weisler frequency. This is essentially telling you the frequency of oscillation, of a vertical oscillation of a parcel of fluid that is oscillating about its equilibrium position in the stable layer. One can equivalently write a timescale for this oscillation, but it's just telling you how strong is the stratification. Now, I mean, why is this important? Well, if we think back to our observations, we're obtaining observation. This is now the top right figure, which I would point to if I could. Our observations are being taken at or above the surface of the planet. And then if we assume that the sort of silicate part is an insulator, we can downward continue our observations to the surface of the core, but we can't continue the observations inside. So what we're learning from our observations is about the very top of the core. So if the dynamics at the top of the core are different, i.e. if we've got conduction rather than convection, we might well expect that, the inferences we make from our observations will change. Okay, so the key thing about these stable layers, they suppress radial motion, they don't help to generate magnetic field. And their evolution is determined by the slow evolution of the core and the mantle, the billion-year evolution, which is going to be important for us. So just to give you an example of what these layers might well do, or what people think they they will do to magnetic fields. This is a nice example from a study by Gastine and co-workers. So these are 4 simulations of dynamo action in a configuration that's been set up to mimic Earth's core. And they are all the same, except that as we go from A to D, the strength of an imposed stratification in the top couple of 100 kilometers of the core is being increased, as measured by this Brunt-Weisler frequency. And each of these figures is partitioned. At the right side, you're looking at the magnetic field at the base of this stable region. So this is what the magnetic field associated with the dynamo process looks like. And then on the left-hand side, you're looking at the magnetic field that you see at the surface of the core, which is the magnetic field that in principle is the one that we observe. And so what you see is that as when you've got a fully convective core, the whole thing's turbulent, generating magnetic field, the strength and scale of the structures in the field are comparable between the convecting region and the surface. But as we increase the strength of the stratification, the field that we observe becomes weaker and it becomes smoothed out. So this stable region is effectively acting like a filter. It filters out anything that's fast, anything that's small in scale, and gives us a smoothed version of the actual magnetic field that we would like to be able to probe with our observations. So I guess that's one key point about these stable regions. They screen the observable field, they will change its amplitude, right? So if we're looking to match the amplitude of an observation, this could be a key process. The other point about the stable layers, which I've already mentioned, is they reduce the power that is available to the dynamo process because there is a part of the core that is no longer helping to generate magnetic field. So to the aims of this talk. So what we've been trying to do is develop a framework that enables us to sort of quantitatively model the long-term coupled core mantle evolution of terrestrial planets with a variety of aims. So to predict the evolution of layers in planetary cores. So this would be an inner core layer, but also these stable layers. We want to constrain the conditions that support dynamo action in these different planetary cores, and then through this process, infer the properties of deep interiors of planets that are not otherwise sort of amenable to direct observation. So what I'm going to do for the rest of the talk, I'm going to give a brief outline of the methodology, and then I'm going to present the 3 applications. We're going to talk about first Mars, Mercury, and Earth. And for each of them, I'm going to first set out the observations that we're interested in reproducing, and then tell you a bit about our results. Okay, so just a bit about the method. I don't want to go into too much detail on the method, but it seems remiss to not say anything at all. So what we're doing, because we're looking at very long time scales here, 4.5 billion years, we solve a model in 2 dimensions, which is radius and time. And the governing equations are essentially energy balances. So if we look at the balance for the mantle over here on the right, it's essentially that pie chart that I showed earlier. So what's happening is that the total heat coming out of the convecting mantle, Q surf, is balanced by all the internal heat sources. So we've got the QS, the secular cooling, QR, the radiogenic heating, and then QCMB, the heat that is coming in through the core mantle boundary. And these, the surface terms, the QCMB and Q surf, they are parameterized. They're using this thing called boundary layer theory, where we write the heat flows in terms of quantities that are sort of local to the core mantle boundary. The model uses an Arrhenian type viscosity, and it operates in 1 tectonic mode. So that would be stagnant lid for Mercury and Mars, and it would be plate tectonic mode for the Earth. So for the core, it's sort of a similar story. The heat balance is exactly the balance that I've essentially already shown you, where the heat that's coming out of the core is balanced by 3 internal heat sources: the secular cooling, so this is just the stored heat, the latent heat that's being released as the inner core grows, and the gravitational energy, which is due to the uneven partitioning of the elements that preferentially go into the liquid phase. The core is approximated as being following an adiabatic temperature. It's chemically well mixed, it's hydrostatic. The reason for this is because the anomalies that drive convection, the thermal and chemical anomalies, are absolutely minute compared to the absolute temperature and the absolute mass fraction. So they can sort of be safely ignored when at this level of approximation. The key thing to note, well, there's a couple of key things to note, actually. So these two heat balances, they couple the core and the mantle together. So one can imagine that once we've figured out the CMB heat flow, we can now pop it into this top equation, and that allows us to figure out the cooling rate of the core, dTc by d time. This thing A is just an integral over core properties. I'm not going to go into its details, but then as the temperature of the core changes, this feeds back into the heat flow through this delta T, and so we get a coupling of the core and the mantle through the heat flow and the temperature at the core mantle boundary. The other thing to note is that, of course, we want information about the magnetic field, but the heat balance, the top equation on the left, it doesn't give us any information about the magnetic field. And that is because magnetic energy is converted into heat internally within the core. So if we want access to some information about the magnetic field, we've got to do something else. And one thing that we can do is write down an entropy balance, because when we write down the entropy, we have access to the irreversible dissipative processes. And it turns out that's where the magnetic field appears. So here, for each heat source, we get an associated entropy term, ES, EL, EC, and these are essentially the heat source multiplied by a thermodynamic efficiency factor, which is sort of telling you about how efficient this heat source is at producing entropy. And again, these can all be written as proportional to the cooling rate. But the key thing is on the left-hand side, you get two positive definite terms. These are the dissipations. The EK is the entropy that's conducted. So this is essentially power that is not available to the dynamo process because some heat is being conducted out of the core. It's not available to drive convection. And then this thing EJ is the thing that we actually want. It's essentially the power that's left over. It's everything in the system that is left over for magnetic field generation. And it's nice because it comes with a sort of formal lower bound that one needs to satisfy in order for dynamo action to be maintained, where the precise value of this bound depends on the particular body that we're interested in. Ooh. My screen's gone off. Ah, there we go. Okay, so just to say something about the stable layer calculation. I guess one thing I wanted to point to was the fact that we spent a while writing a sort of, well, what we consider to be a relatively flexible code for solving diffusion problems subject to moving boundaries. It's here, so if you want to use it, you can just download it from GitHub, play around with it. There's examples and stuff to have a go with it. So what it does is it models it models the evolution of this stable region. It's been tested against a whole bunch of benchmark solutions, so analytical solutions where you've got radially varying properties in a sphere, and we've also reproduced published work with it and so forth. I guess the key technical point for those who are interested in technical points is that how you figure out where the stable layer is not entirely straightforward, because if you had a nice classical Stefan problem, then there would be an additional condition, mathematical condition due to the melting that would tell you exactly where this interface is. But we don't have that condition. But we do expect that there is continuity of temperature and heat flow at the base of the layer. And so what one can do is use one of these conditions to solve the diffusion problem and another one to figure out where the layer is. And that's the sort of basic approach. But like I say, anyone who wants to play with it and give us feedback, the code is freely available. All right, that's all I want to say on methods. So let's talk about the actual application. So we're going to do Mars first, then Mercury, then the Earth. So the primary observation for Mars that will be of interest in this talk is the time when dynamo action in the liquid core was inferred to have ceased. So that's sort of being shown on this rather complicated top plot. It's inferred from magnetism acquired from Martian meteorites. It's also inferred from the magnetization or lack of that is found in ancient impact basins. And the basic result, for the purpose of this talk at least, is that the global magnetic field is inferred to have decayed somewhere between 3.6 and 4.1 billion years ago. The exact value is not going to be of critical importance for what we're going to do. And there's been various ideas about why this happened. So an early suggestion from Nimmo and Stevenson was that perhaps there was an early episode of plate tectonics that subsequently plate tectonics stopped, stagnant Lig convection started, the reduction in heat flow caused the loss of dynamo action. The problem with this, I think, is that subsequently there hasn't really been any evidence found for an early episode of plate tectonics, and so it's been largely discarded. Another option is that perhaps Mars grew an early inner core. So with all this latent heat and gravitational energy powering the dynamo, we get an early dynamo, but at some point the solid inner core would freeze out most of the liquid core. There'd be no liquid to generate the dynamo. The problem with this is that this is contrary to geodetic observations that we have showing that at least some portion of the Martian core is currently liquid. And it should be pointed out that a present inner core is not incompatible with the dynamo observations, but it is difficult to have an early growing inner core because we would have frozen out most of the liquid region. So the idea I think that most people have run with is that during the formation of Mars's core, additional heat was implanted into the core, so the core was superheated compared to the mantle. This heat was lost in the early history of Mars, and once that heat was consumed, the Martian core became conductive, stopped generating a magnetic field. And this is the sort of idea that, it's the sort of idea that we have pursued here. So what we did, I guess the question is, why redo this? It seems like a fairly well-established story. We focused on three factors that didn't seem to have received much attention in the previous modeling of Mars's core. So the first thing we wanted to do was self-consistently account for the stratification in the core, because almost all previous models of Mars's core had just assumed that the core essentially continues to be convecting, even though it's not. So we wanted to get this self-consistently right using the method that we've developed. Also, more recent experiments that are at temperatures close to Mars's core mantle boundary and at slightly lower pressures infer a reasonably low thermal conductivity for some of the materials that could plausibly be in Mars's core. So these are alloys of iron, sulfur, oxygen, and so forth that are on the plot up there. There's a range of conductivities that one would infer of about 5 to 30 watts per meter per Kelvin, whereas a lot of previous studies had used much higher values, 40 watts per meter per Kelvin and above. And the final thing is that is sort of enabled by point one is to try and use additional constraints where possible on the evolution of Mars. So traditionally, the only constraint that's used is when the dynamo terminates. And of course, you can imagine that a wide class of models are able to satisfy this constraint. But there's been quite a lot of work done on Mars's interior structure, and in particular, inferences of the temperature at the top of the convecting part of the mantle. And since we now have a sort of more accurate description of the core temperature, this is going to give us access to using this constraint, which is going to turn out to be quite useful. Some details on the model. So we're considering an iron nickel sulfur alloy. We took the melting point from Guilfoyle and Lee, and with this melting temperature, it turns out that none of our models ever form a solid inner core. So the actual equations that we have to solve for the core are much simpler. We have no latent heat or gravitational energy. A simple heat balance is here. We took the insight structure, so essentially things like the density, the size of the core. So the model is automatically consistent with these constraints. So for the core, we varied the thermal conductivity. We also varied its initial temperature, and we varied the initial temperature of the mantle because these are not well constrained by any observations. The mantle model is relatively simple. It's sort of shown in 1D form on the right. It's a stagnant lid model of mantle convection. There are two boundary layers. There's one just here, and there's one here, which is the part of the stagnant lid that is participating in the convection, and then there's a conductive piece at the top. And so we varied two properties of the viscosity profile, the reference viscosity and the activation volume, which is essentially determining the pressure dependence. And what we want to do is compare to these two constraints. We want to find models where the dynamo fails in this particular time period inferred from the observations, and this corresponds to this dynamo power falling below its minimum value. And we also want to find models that can match the inferred upper mantle temperature. So here's an example of three different runs. They're all time series, so time is on the horizontal. You've got heat flow on the left, this dynamo power up on the top right, and the radius of the stable region normalized by the core's radius on the bottom right. So if we take first of all the red curves, this is what we called our reference model. Its parameters are at the bottom for people who like parameters, they're all there. What happens in this model, if we focus on the heat flow first, is that the heat flow rapidly declines near the start as the superheat is being extracted, and the solid line falls below the dash line, and that is where the heat that the mantle is extracting from the core falls below the heat that is being conducted out of the core. And so this stable layer starts to form. Okay. The stable layer actually ends up keeping the core, the top of the core, warm because you can't get the heat out essentially. And so that actually ends up elevating slightly the CMB heat flow. But what happens is that the power falls below its minimum value in this window that we were hoping for. Well, I guess that is constrained by the observations. And so this model is an example of a sort of a successful model. It can match the available constraints. And it turns out in this model, the entire core of Mars is stably stratified by the present day. There is no region that is unstable to convection. The next model, which is the blue one, is just the same as the reference, but the thermal conductivity has been reduced quite dramatically to 5. The difference between these two lines is showing the effect of the stable layer. These two would be identical if there was no stable layer in the calculation. So the stable layer keeps the core hotter, which enhances the heat flow. But the main problem with decreasing the thermal conductivity, at least here, is that the core remains convecting everywhere, even to the present day. So the solid line doesn't intersect the dash. And when we look at the power, the model is essentially predicting that there is dynamo action in Mars to the present day, which is problematic. The final model is the black one. Here we've increased the reference viscosity. What happens here is that this stifles the heat flow coming out of the core. The heat flow falls dramatically at the start, and that causes the dynamo to fail too early. So of course, you can run a whole load of models, and that's indeed what we did. And we produced these plots here. So we'll start with the one on the left, because this is looking at our two constraints. So this is the time when the dynamo terminated on the vertical, the upper mantle temperature on the horizontal, and the log of the reference viscosity in the colors. And the lines are showing the constraints. And so where we've got the box is the region where the two constraints are satisfied. So what you can see is that the time when the dynamo fails is pretty insensitive to the reference viscosity, and that's just because you can change the other parameters to get the dynamo to fail in the right time period, which goes back to what I was saying earlier. When you've just got the one constraint, you can find lots of parameter combinations that match it. However, the present mantle temperature is very sensitive to the viscosity, and that's because the viscosity is determining the heat extraction. It's determining how fast the mantle is cooling. So this constraint on the temperature is giving a strong constraint on the viscosity, which of course we don't know and would like to infer. So on the right, time when the dynamo failed, again on the vertical, core conductivity on the horizontal, and the colors are showing how much of the core is stably, firmly stratified. So now we can see that the time when the dynamo fails is strongly sensitive to the thermal conductivity, as we would expect. And of course, so what's happening here is that as we go up to higher conductivities, we're able to find more and more models that satisfy the constraints. When we're at very low conductivity, we're in the situation of the blue line on the previous slide, where the dynamo just lasts forever, which is unreasonable. And what's happening is that we're in this region where most of the models are successful. We're finding that most of the core is stratified. There are some models where there's some portion of it that's not. Most of them actually are. And there are these two branches here that are at a low core conductivity, where essentially it's due to this flattening out of the heat flow curve. Essentially what's happening is that the dynamo can either fail very early or very late because of the shape of the heat flow curve. But one of the things we observed, I guess, that the main things we observed is that using these two constraints, we found that you could get relatively tight bounds on the reference viscosity and the thermal conductivity, and that we found that the core was quite strongly thermally stratified at the present day. So this is a bit of a dry slide, but it summarizes what we did, because of course we didn't just run those models, we ran some other ones. So the quantities that were of interest are written on in the left column: the thermal conductivity, reference viscosity, how much of the core is stratified, and the numbers that are being given in these panels are the ranges of successful models that matched both the constraints. And there were 4 different types of model that we ran, and what we were doing was changing the pressure dependence of the viscosity and the abundance of the radiogenic heating. So essentially how much additional radiogenic heating the crust has got. And what we found, I guess, from doing all of this is that, once you've run sort of 500,000 models, there were still relatively well-defined ranges of the thermal conductivity and the viscosity that could be satisfied sort of regardless of how you set up the model. And we also found that in the majority of cases, the present day core is quite strongly stably stratified, and in some cases even fully stratified. Okay, Mercury. Oh gosh, we've got 10 minutes. Mercury. Okay, so I've talked about 2 of the observations. One is it's got a weak field at the present day. The second is that there was potentially an early dynamo, so perhaps the dynamo has been operating for a long time. There are 2 other constraints that we're sort of interested in. One is that there are a sort of global sequence of shortening structures that are inferred to represent about 1 to 10 kilometers of radial contraction of the planet, and that the present day crust is about 15 to 60 kilometers thick. So these are the main constraints that we're interested in. There is some evidence of temporal variations in these constraints, such that the crust was formed early, but these are still sort of a bit up in the air, and we've just sort of taken present day values. Okay, so most studies up until about 2018 assumed that the core was an iron sulfur composition, and this is crucial because sulfur partitions, at least at these conditions, very strongly into the liquid, so you get a load of gravitational energy. But it's now thought that Mercury formed under highly reducing conditions, and in that case, its sulfur actually wants to stay in the silicate phase as the planet forms, and instead silicon wants to go into the metal. And silicon tends to partition almost evenly between the solid and liquid core, and so this contribution, this really efficient contribution to dynamo action, is gone. So Nibber and Van Vestrenen investigated this, and they were really the first to show that when you have this iron silicon core with this quite different core evolution, you can still produce long-lived dynamo action in this case. What they did, though, they didn't consider the contraction as a constraint on their model, and it will turn out this is quite an important constraint. Peterson, actually, they did look at the contraction. They looked at all 4 of the constraints that I've mentioned, but they didn't actually consider the growth of an inner core or a stable region, and these 2 actually do affect the thermal evolution quite a lot. So what we wanted to do was consider all 4 of the constraints that I've mentioned, and with the self-consistent layer calculation I've talked about. And we were also interested, because there might well be a little bit of sulfur in the core, on this possibility of the formation of an immiscible region near the top of the core, where we've got a sort of low conductivity iron sulfur layer sat atop an iron silicon bulk core. So the model, this is sort of similar to what we did for Mars. The model's a bit different. So we used the iron silicon melting curve from Edmund. Structure is from a recent interior structure model. As I've said, there's no gravitational energy, but there is plenty of latent heat from the inner core to power the dynamo, and this turns out to be a very effective method of generating the magnetic field of Mercury. We varied a bunch of parameters, so the thermal conductivity, initial core temperature. We looked at a range of silicon concentrations, and when we added in the stable layer, it has a low thermal conductivity compared to the bulk. The main thing that we varied, the mantle model is a little bit more complicated. I won't go through the details. The main thing that we varied was the viscosity, the reference viscosity, because this changes the heat flow out of the core and hence the power to the dynamo. And we're looking to match these 4 main constraints. So here are some examples of the solutions. Again, it's sort of analogous to the plot that I showed for Mars, 3 time series, heat flows on the left, power to the dynamo, stable layer, and now the inner core radius on the bottom here. So a bit like Mars, you get the growth of a stable region very early on. So if we take the reference case in red, the heat flow being pulled out of the core rapidly falls below the heat flow that's being conducted out of the core, so the dashed line. So you get this early formation of a stable region, which you can see in the curve over here. But you also, in Mercury, end up getting the formation of an early inner core. Okay, and so in these models, what happens is that in the reference case, we get quite a narrow convecting region at the present day that is nevertheless sufficient to be generating a magnetic field. And the magnetic field is generated over all of time because the latent heat release associated with the inner core growth is very efficient. I guess the other one that I want to point out is the black line, which is where you decrease the reference viscosity. And now we have a lobe more heat being pulled out of the core. This causes the inner core in particular to grow much too fast, and you end up sort of freezing out almost all of the core by the present day. So these are plots of our 4 constraints, and they're all against the reference viscosity. And it looks like what's in the color is the silicon concentration, and it sort of looks like there's a lot of information, but actually everything boils down to this plot here, the amount of radial contraction. If we want to get 1 to 10 kilometers of radial contraction, we need a high reference viscosity. And that is because this is just stopping the cooling of the core. It turns out that most of the contraction is due to the growth of the inner core. And so a high viscosity allows this to happen. And it turns out that when you're in this high viscosity regime, you actually get all the other constraints sort of for free. You get a reasonable crustal thickness. So the dashed lines are just showing you the bounds. So you get the crustal thickness, and you get a dynamo that operates for all of time because the inner core comes in nice and early. So this contraction constraint is absolutely crucial. What you learn from the model is that these are just all the successful models here in these 3 panels. So they're just the ones that are here. The stable layer is thick. It's a few hundred kilometers. The inner core is thick. It's about 1,000 kilometers or more. So in Mercury at the present day, these models would predict that there is not a very large convecting region. We have 2 very thick layers. And the other thing to notice is you do produce a weak magnetic field, but it's not as weak as the observations suggest. And I'd be happy, I haven't got time to talk about why that is now, but I'd be happy to chat about it. So just finally, and finally the FES layer. So what we did here is we just added in 2 FES layers of 2 different thicknesses, 10 and 100 kilometers. They've got a low conductivity, but really the point is very, very simple, which is that from the perspective of our model, adding in this layer makes absolutely no difference. It makes no difference to the power that's available to the dynamo. It makes no difference really, or very little difference to the properties of the layers in the core. So for at least from the perspective of this model, the model can't really place any constraint on the properties of an FES layer at the top of the core. The dynamo evolution is essentially unchanged. All right, so a few more minutes for Earth. So in Earth, we have seismology. So we have a means to probe the seismic structure, at least, of the top of the core. In particular, there are these nice set of waves, SMKS waves. So they are waves that are reflected m times underneath the core mantle boundary. And by differencing travel times of different m's, you can probe the structure near the top of the core. Now, it should be said that the actual geographic bias, there's a strong geographic bias to the available observations. A lot of the wave paths that actually traverse the core are in the Pacific region, and this is going to come back to be somewhat important. But what's mostly been done is that these observations have been interpreted as a global layer. And when one interprets them as a global layer, what you infer here is a reduction in the compressional wave velocity compared to your 1D model, which is PREM, which is very, very close to being the sort of adiabatic, hydrostatic, convective state of the core. And with this reduction in the velocity implies an anomalously, the slowness of the layer implies that it is stably stratified. What you infer is that the stratification is actually really strong. There's quite a few assumptions that go into this, but if you take a sort of chemical model of the core involving silicon and oxygen, you figure out that actually this stratification is very strong. Now, what you'd like to do is be able to use geomagnetism to try and back this up, because we're generating a magnetic field, and generating that magnetic field requires some radial motion. Now, from a purely observational point of view, this is difficult. Formally, the error on the flow obtained at the top of the core at a point is unbounded. What is known is that you can fit most of the secular variation. So this is the change in the recent magnetic field. You can fit most of it with a purely horizontal flow, but you improve things if you add in a bit of radial motion. But what dynamo simulations suggest is that they really don't like stable layers. This is the same study that I showed you earlier by Gastine. And if you recall, what happens is the magnetic field, as you increase the stratification, it becomes smooth and it becomes weak. And so what you can do is you can compare the similarity between the field that you've synthesized from your dynamo simulation and the field that you observe. And you can do this quantitatively using a set of criteria. And as you increase the strength of the stratification, the agreement goes down. And of course, that you can't reach Earth's core conditions in these simulations, but if you were to extrapolate, you would find that actually it would be preferred that there will be no stable layer at all. Or if you have one, it should be weak and relatively thin. So we looked at this. We essentially just performed the same set of calculations that I've shown for Mars and Mercury, 2D type calculations, to look at what types of stable layers are commensurate with the observations. So this is the present day heat flow. If you're in the gray region up here, you're convecting all the way to the top. You've got no stable region. If you're in the white region, your dynamo fails. You've got too much stable layer. But what you find is that you can quite happily produce stable layers that are 700 kilometers thick. This is easily thick enough to match the inferences from seismology of 400 kilometers. So from a thermodynamic point of view, you've got no real problem, and you've got sufficient uncertainty on the heat flow that it's possible to produce a thick, stable region. Now, in terms of the strength, just by having a thermally stable region, it is hard to match the strength of the stratification that you infer from seismology. There are a bunch of other inferences. This one by Buffett is based on waves. This one is based on dynamo simulations. So you can do a fair job of matching the amplitude of the stratification. These delta rho's here, this is essentially governing how strong is the gravitational energy in the model, but it's not particularly important for the conclusions. So if you just vary all the parameters, given their uncertainties, and subject to the constraints that we've got a dynamo and we've got the correct inner core size, you can find thick stable regions that are totally in line with the observations. You can't get them quite strong enough, but you're in the right ballpark. But you've nevertheless got this issue that the dynamo simulations would really quite like there to be no layer at all. So I guess just finally, I want to talk about some ideas that we had about how to potentially reconcile this issue. So in the Earth, it is pretty well established that at the base of the mantle, there are two large low velocity provinces underneath Africa and the Central Pacific, and that at least in simulations of mantle convection, these regions are anomalously hot compared to ambient mantle. And likewise, regions where there are subducting slabs tend to be anomalously cold, and this produces variations in heat flow at the core mantle boundary that the dynamo must respond to. This is a particular example of an inferred pattern of heat flow. So the heat flow is anomalously low under the large low velocity provinces, anomalously high in the ring of fire surrounding the Pacific. And so what this is doing is forcing the core to take out more heat in certain regions and less heat in others. And it turns out these lateral variations in the heat flow can be really strong, like 2 to 30 times the average. And so what we did is we ran a bunch of consistent, self-consistent convection calculations. These are now fully three-dimensional with this pattern of heat flow imposed. And what we found was that you have all this turbulence underneath. This is what would be generating the magnetic field. But these, at the top of the core, you can get these very strongly stabilizing regions. We called them regional inversion lenses. It's shown here. So the temperature gradient in the convective regions is strongly destabilizing. But when you take a transect through one of these regional inversion layers, the temperature gradient becomes strongly stabilizing. And so the sort of question was, well, can you have your cake and eat it? If seismology is seeing these regions, it would see strong, stable stratification, but you can still have your radial motion because you've got regions that geomagnetism wants, because you've got regions where you've got convection all the way to the top of the core. It turns out that you can do a nice little bit of theory that collapses a bunch of these simulations that allows you to predict the strength, which is on the top, and the thickness, which is on the bottom of these regional inversion lenses, and extrapolate them to planetary core conditions. So that gives you the star and the square here. And we get thicknesses of 1 to 300 kilometers, perfectly in line with what you get from seismology. Strengths of, where again, using the Brunt-Weisler frequency, comparable to what you get from seismology. And also in, you get regions where you've got weak stratification, which is what you want from geomagnetism. And there's just one more thing I want to say about these, about this idea, where now that the stratification is regional rather than global, which is it has some nice properties that you can actually match characteristics of the modern magnetic field in quite a lot of detail. So what I'm showing here, the radial component of Earth's magnetic field and the radial component of our simulation, both at the core mantle boundary. So now you can see a lot more structure because it's been downward continued from the surface of the Earth. We get quite good agreement. It's dominantly dipolar. There's flux patches in approximately the right places. And this is not surprising because it's well known that simulations can reproduce the large scale features of the magnetic field morphology. What is much harder to do in simulations is to produce the morphology of the rate of change of the magnetic field. We have good observations of the rate of change of the magnetic field over the past 30 years. And what you find is this quite characteristic hemispheric pattern where all the variability is in the equatorial Atlantic. The Pacific tends to be rather quiet. And sort of there's only really been one example, at least in detail, of a simulation that managed to produce this particular pattern. But it turns out that a pattern quite similar to the observations emerges naturally from these simulations that involve regional stratification. And the reason it emerges is because of this characteristic flow structure that I wish I could point to, where the flow, is coming westward and then diverges around the central Pacific. And this is a flow that is really quite similar to what you find from inversions of the magnetic secular variation. So these simulations, at least to the level that we've analyzed them, have a few properties that are quite desirable. They can produce sort of a reasonably detailed agreement with the modern magnetic field, and they give you regions where you can be both stabilizing and destabilizing, which might help to reconcile the seismic observations with the geomagnetism. Okay, so what I've tried to convince you of is that planetary cores can form these stable regions at the top, where stable regions that are not participating in the dynamo process, and that these regions might be important for understanding the observations that we have. So in the case of Mars, we were able to constrain the thermal conductivity and the reference viscosity of Mars, to within the assumptions of the model. And at least in Mars, we found that most of the core is thermally stratified, which might well be useful for interior structure models that have to assume a temperature profile in the core. So for Mercury, there are these four constraints to do with two to do with the magnetic field, one to do with the contraction, one to do with the crustal thickness. But it turns out, at least in our model, that the contraction is absolutely key, and that constrains the viscosity of the mantle to be quite large. And we find, again, that the present core contains a thick, stable layer, but it will also contain quite a large inner core. And that the FES layer didn't really do anything in our simulation. So the simulation was not able to constrain its properties. And then finally, for Earth, the stable regions are often interpreted as global layers from seismology. And when you sort of perform the same calculations as we did for Mars and Mercury, then you can get reasonable agreement with the observations, the seismic observations, but you still have this issue that dynamo simulations would much prefer there to be no stable region. And we suggested this, one way out of the apparent conundrum, where we can have regions that are stabilizing and regions that are not. And I'm going to stop there.
Check. Questions? Is this working? Is this mic'd up? Here, start with Mike and we'll go to Faye.
All right, thank you so much for this cool talk. I really love all the simulations. Help me understand Mars a little bit. So you say that the core is basically thermally stratified throughout, so it's not convecting.
Yeah.
And then you linked that to a scenario in which Mars's core was superheated and then cooled very quickly. Tell me more about that. Why would a superheated core cool super quickly and then become thermally stratified sooner than a not superheated core?
I can answer the first bit. So when it's superheated, you've got a large temperature difference across the lower mantle boundary layer. So that's going to give you a correspondingly large, and because you're hot, the viscosity of the lower mantle is going to be low. Those things are all going to give rise to a large CMB heat flow. You're going to pull heat out of the core fast. As you do that, you cool down the core and the mantle, the viscosity increases, the heat flow eventually plateaus.
I see. So there's the feedback between the temperature and the viscosity. Yes. Okay. And why would Mars be superheated to begin with?
Well, ain't that a question? I mean, that is going to depend on the details of how it formed, isn't it? And so, I mean, which is going to be a very complicated process that, so, I mean, I don't have a good answer to that.
Okay, no worries.
I think, we varied the superheating, following previous work.
Okay, cool.
This is really interesting, and particularly I like the consistency, self-consistency. But my question is on your Mercury model. So if you think about the core evolutions, obviously you start with a liquid core and then solidify. And so my question is really, if you look at the strengths of the Mercury, would you predicting some variations? And particularly if you think about the stable layer, it can't be like come out of nowhere, right? It has to be associated with some kind of internal. Are you saying the stable layer is, would you say the stable layer is coming from the inner core solidifications, or there's no relationship?
We're talking about the thermally stable layer at the top.
Yeah. So how, my understanding, the thermal layer is going to correlate with the strength of the magnetic field.
Yes.
Right? If that's correct?
Yes.
So if that's the case, then how would you predict from your model and through the histories and the Mercury strengths and the varies and how it will correlate to the stable layer? Okay, so this is a very good question. So what I deliberately set this model up in a way that what we're finding out is the total power that's available to the dynamo. If we want to go from the power to the field strength that we observe, there are several different steps that one needs to be able to go through. First of all, one needs to establish what they consider to be the dominant balance of forces in the dynamo. That tends to be considered to be the so-called Mach balance, magnetic, Archimedean buoyancy, and Coriolis, and that will give you a scaling relationship between the internal field strength and the power that's available to the dynamo. You then need to figure out how the internal field strength maps to the dipole field that you observe. And dynamo simulations tend to suggest that the dipole, the observable dipole is about
15 times weaker than the internal field. And so when I showed the plot of the intensity of Mercury's field that was predicted from the model, that is what I'd done here. But I'm pretty confident that one or more of those assumptions has broken down in order to, is incorrect. And I think people have found this before.
No, the question on Mercury, given that Mercury is in a 3 to 2 spin orbit resonance, its rotational period is much longer than that of the Earth. So isn't that thought to have some sort of effect on the fact that Mercury's field is 100 times less than the Earth's?
Yes, it is. But I don't know, I had a little look at this and I was pretty, so we normally measure that, we think about the rotational effect of the Rossby number, which is the ratio of the inertial term to the Coriolis term in the equation of motion. And for the, I mean, it's a bit difficult in terms of how you estimate it, but I guess for Mercury, it's more marginal. Like for the Earth, it's 10 to the minus 6. So the rotation is absolutely dominant over the inertia. For Mercury, it's closer to 1. And previous studies have found that Mercury would generate a multipolar field. And this is what you would get if the inertia is too strong, essentially. And that is another reason why perhaps this inference of the field strength is wrong, because what I've done is assume that the inertia is irrelevant when in fact perhaps it isn't. And of course, I would get a different relationship between the power and the observed field strength if I had accounted for the inertia as opposed to the rotation.
Thanks, Chris, for a very, very nice talk. I think I'm gonna have to watch it again. Could you fast forward to the model of Earth and the LLSVPs, just the sort of, yeah, that picture there, perfect. So if I'm understanding correctly, the stable layers here are regional.
Yes.
And they're beneath the LLSVPs.
Correct.
But doesn't seismology indicate that the layers are global, or is that just a model that they're global to fit?
They are, it's assumed to be global.
It's assumed to be global.
Correct.
Okay, so this prediction would say it's not global.
Yeah.
And therefore we should be able to detect that seismically if we're looking.
Yeah,
for
the
it.
prediction from the model, well, I mean, I guess the call to arms is to reappraise the seismic data in the context of regional variations rather than assuming a layer.
Okay, and so doesn't Earth's magnetic field strength increase substantially around 700 million years ago, something like that?
Depending on when, yeah.
Is that, well, my question is that then likely related to this regional layering in some way, that might give you a signal of when the LSVPs formed, which would be contrary to most modern kind of views of it, but
it's a really good question, because what most theoretical models find is that you will get an increase in the field strength when you form the inner core because of the latent heat and the gravitational energy. Now, in the paleomagnetic record, you have a well-established high field at 1.1 billion years ago, which is from the Mid-Atlantic Ridge. And then you have the crazy low fields in the Devonian and the Ediacaran, and you have the present field, which is high.
Mm.
So you've got a bit of a problem, which is you've got a high at 1.1 that then went really low, that then came high again. And you've only got one in the core to give you the high. So it's a bit tricky. If you say the inner core formed early at like just before 1.1, gave you the Mid-Atlantic Ridge high, then you can't explain the low fields in the Devonian. Likewise, if you say it formed later. So, I mean, I guess the answer to your question is potentially, because there needs to be another process that can be invoked to explain the two highs.
great, thank you.
Okay, Bob?
Yeah, Alan asked my question.
Oh, okay. Anybody else? I ask a quick question. In your thermal models, when you change the thermal conductivity, does that also change the electrical conductivity?
The electrical conductivity doesn't appear in the model
Well, it's in the ohmic. Oh, the ohmic dissipation comes
because we
out.
get the total ohmic
Okay.
dissipation, which is the integral of J squared.
Okay, but if you were to back out the field strength from the ohmic dissipation,
Then you have to assume a conductivity, yes.
yeah, and when the thermal conductivity is low, you would infer.
Although,
extra-
do you actually? No, because for the we're going a bit technical here, but
Yeah,
for the
okay.
Peter Davidson 1/3 scaling, I think it's diffusionless.
Okay, that is in the weeds.
So that means that, so the conductivity in that case comes in as a magnetic diffusivity and the scaling is diffusionless.
Yeah, okay.
So I think it's not there.
All right. Well, we'll be at lunch. We can talk more and he's here till Thursday. So if you want to talk, let me know. Let's thank Chris again. Probably kill your mic now.